Hello, y'all, and welcome back. This is Lesson 5, Structure 1.2.2, and we're going to be covering isotopes. They're atoms of the same element with different numbers of neutrons. We're going to be able to perform calculations involving non-integer relative atomic masses and abundance of isotopes given from data. And we're also going to briefly discuss differences in physical properties of isotopes, and we'll actually be able to explain that more later on as we cover intermolecular forces. But without further ado, let's begin. So when we talk about isotopes, the first thing we need to note is our periodic table. Now, in our periodic table, usually we have these boxes, about 118 of them, and they have a couple things. The first thing is we have our atomic number. From the previous lesson, our atomic number is the number of protons, and that number identifies the element. So every element with the same atomic number is the same element. Then we have our element symbol. It also identifies the element. It's always going to be 1 to 2 letters, 1 to 2 letters, and the first one is capitalized. First one capitalized, always. Always, always, always. And then lastly, we have this number at the bottom. That is our relative atomic mass. Now, the weird thing about the relative atomic mass is that it's pretty much always going to be a decimal, which is wild because where does it come from? Where does it come from? And what I mean by that is that we know that the relative mass, as described in the previous unit, relative mass can only come from protons or neutrons because they both have a relative mass of 1. Electrons have a relative mass of 1 over 2000, which we said was kind of basically 0 because it's negligible, we ignore it. So how do we get decimal places in our relative atomic mass? Well, that's due to isotopes. Isotopes, once again, are atoms of the same element with different numbers of neutrons. A great example to look at is hydrogen. Now, with hydrogen, just going to draw 3 little atoms of hydrogen, and I'm going to use blue to denote electrons. Let me just go ahead and copy this a couple times. And these are going to be electrons. We're going to use red to denote protons. They all have 1 proton. And we'll use green to denote neutrons. All right, and these are going to be our neutrons. So here we have hydrogen 1, also referred to as H11. Here we have hydrogen 2. Again, that number representing the mass number. It's the same as the number in the upper left corner. And here we have hydrogen 3. So here's hydrogen 1, 2, and 3. Another word for them each. This is also sometimes referred to as protium. This one is deuterium. And this one is tritium. So we notice with these that we have 1 proton, 1 electron, 1 proton, 1 electron, 1 proton, 1 electron. So they're the same element and they have the same neutral charge of 0. But here we have no neutrons, 1 neutron, and 2 neutrons. So these are different isotopes of hydrogen. So if we were to just chart this out real quick, hydrogen 1, 1, hydrogen 1, 2, and hydrogen 1, 3. And we look at our protons, neutrons, and electrons. We have one proton, one proton, one proton, zero neutrons, one neutron, two neutron, and one electron, one electron, one electron. So they're all relatively the same. And due to this, they all behave similarly in chemical reactions. So they're all going to behave like hydrogen. But the difference is they'll have slightly different physical properties. Slightly different physical properties. Now, what I'm referring to here are like density, boiling point, and melting point. So let's explain these really quickly. We're not going to do much math right now, but density is quite obvious. Density is defined as mass over volume. And if it's mass over volume, and we have a mass of 1, a mass of 2, and a mass of 3 relative masses, then clearly we're going to have different densities, with hydrogen 3 being the densest and hydrogen 1 being the least dense. Let's move on to the next aspect, which is the question we asked earlier. So, where does relative atomic mass come from? How do we get that? Well, it's actually not as bad as you might think. So relative atomic mass, which we use A subscript R. And really quickly, that's not AR. No, no, no. That's argon, the element. It's A subscript R. So make sure that that really is a subscript. So relative atomic mass is based on the abundance of each isotope in nature. So to really understand what that means, I think the best way to do it is by using an example. So let's look at magnesium. In nature, magnesium exists as magnesium 24, magnesium 25, and magnesium 26. So if you were to find an atom of magnesium, you would find one of these three types, 24 having a mass number 24, 25 having a mass number 25, and 26 having a mass number of 26. So if we look at magnesium 24, we find that about 78.99% of magnesium is magnesium 24. If we look at magnesium 25, we find that only about 10.00% is magnesium 25. And for 26, you can figure that out by doing 100 minus that. It's a percentage, which gives you 11.01% magnesium 26. So to find the relative atomic mass, I'm going to give you an equation and then explain it. The relative atomic mass is the sum, so I'm using the symbol for sum, of the mass number times the percent abundance of each isotope. So what that basically means is our mass number of magnesium 24 is 24, and we're going to multiply that by its percent. Now, percent is out of 100, so instead of saying 78.99, I'm going to write the percentage as a number, which is 0.7899. I will add that to 25 times its percent, 0.1000, and I will add that to 26 times its percent, 0.1101. When I plug this all into my calculator, I get 24.32 is the relative atomic mass of magnesium. You'll notice that that's both the number on your periodic table, but also that it's close to 24, which should make sense, seeing as 24 is our most abundant, the most abundant isotope. So that's how we calculate relative atomic mass. So this is the end of the lesson, but what I'm going to do at this point is go over two examples. So if you want to stick around and do the examples, please feel free to. If you want to pause after I write the question and solve it yourself, please feel free to do that as well. So going through examples, number one, bromine exists as bromine 79 and bromine 81. It has an abundance of, oh, actually, that's not this question. It has an atomic mass, so I'm going to give you straight up the atomic mass of 79.90. What is the abundance of each isotope? So this is very much a question that the DP will ask you, and you have to be able to work backwards. So using our formula, I'm going to start with my abundance. 79.90 is equal to the isotope mass, 79, times its percent abundance. Now, I don't know what that is, so I'm using X. I'm going to add that to my other isotope, 81, but then I'd have to have a different percent, Y. I know that my percentages, X plus Y, equal 1, because once again, I'm going to be using decimals. Therefore, y is equal to 1 minus x. So I'm solving basically a systems of equations. You do need to know some pretty basic algebra to get through this. So 79.90 is equal to 79 times x plus 81 times 1 minus x. We're going to solve this out and find that 79x plus 81 minus 81x is equal to, once again, 79.90. Much like in math, it's very important to keep your work organized. We're going to combine like terms and move our 81 over to the left. So I find that I will get negative 1.10 by subtracting 81 from both sides is equal to negative 2x. I will divide by negative 2 on both sides and find that x is equal to 0.55. In other words, the isotope 79 has a percent abundance of 55%. Meanwhile, 81 must have a percent abundance of 45%. So that is question 1. Hopefully you were able to do that. Question 2. We're going to now find the relative atomic mass of gallium, which has an isotope 69, and gallium 71 with a percent abundance of 60.10% and 39.90% respectively. Basically, that means that this 60 goes with the 69 and the 39 goes with the 71. So we're going to just plug that into our equation. Relative atomic mass is equal to 69 times 0.6010 plus 39, oh, whoops, my bad, plus 71 times 39.90, oops, my bad again. Once again, we have to turn these from percentages into numbers. And we find that our relative atomic mass, when you've plugged it in, is going to be 69.80. All right. Well, hopefully you're able to do this on your own, and hopefully this helped you figure out a little bit more about isotopes. Have a great day.